Okay, the last speaker of this session is Flavio, right?
I sorry, I have to interrupt you guys. Yeah. I really apologize for this. That's another talk about some sense at the beginning. We'll be continuing what Ashley was mentioned about the Lib lattices. So I'm interested in quantum criticality in altermagnets. So I'll say that altermagnets are a new problem for me. So I started understanding better now. And this talk is about mostly interacting systems. Let's mention the collaborators. There are two works. There is something that is still unpublished with Toshihiro Sato. There is some published work of Asla, the previous speaker, his student, Sondra Lundamo, who did many of the calculations shown in this talk. I want to start by recalling some very well-known facts about the Hubbard model at half filling. How's the mean field theory in a square lattice, only nearest neighbor hoppings in the Hubbard model at half filling? So this square lattice here, I put intentionally 45 degrees respect to the vertical here, just because I've introduced things related to the previous talk in that slide. So if you remember this, you take this nearest neighbor hopping. If you have only nearest neighbor hoppings, you can make the lattice will be bipartite. You have a hopping only to B, C sublattices. And here there's my Hubbard interaction with half filling is exactly given by mu equals U/2. So by standard methods, mean field theory methods, doing Hubbard Strokonovich transformation, etc. Here their spins are defined in terms of fermions and Pauli matrix. It's very easy to derive this gapped spectrum. You will see that it's a spin degenerated because S, the spin, the sublattice magnetization have spin up and spin down here. This is the ground state, so appears square. Now, this is the standard, this is gapped for all values of the interaction. So of course, there is a metal insulator transition. We know that, but this is beyond this simple mean field approximation. Now what I will do, I will add, this is nothing to do with automagnets yet, but what is the mean field for the same theory if I would have a spin splitting? Because here there is no spin splitting, this is a spin degenerate. So I will include additional sites to this lattice by the alternate way in the square plaquettes, so with these blue sites here. Right? In this blue sites, which are called A, but not a sublattice, will be again, like in the previous talk, 3 atoms per unit cell. I don't have a Hubbard interaction there. This is a toy model, of course. I didn't put a Hubbard interaction here, but this is intentional because I want that these blue sites to be non-magnetic at the end. And now, if this lattice is kept bipartite, this means only nearest neighbor hoppings. This means there are only hoppings from A to B or A to C, but not from B to C like in the previous slide, right? So this is like in the previous slide, I have this T1 here, you see? So this would be at half filling ferrite magnet. This is a result proven by Lieb 30 years ago. So it's not alpha ferromagnetic any longer. However, if T1 is different from 0, you have this hopping between A and B and A and C. In addition, it also, so you have next nearest neighbor hopping, so the lattice is not any longer bipartite. So then you will have spin splitting bands, which are essential to automagnetics. But this you see, mean field theory, the opposite that happens for the bipartite lattices. So it doesn't matter how large your U is here. Here again, 2 is applied values 1.3 times T. 1.6 times T, there's still metallic, there is no gap here for half filling. So to summarize this part, you see that mean field theory at half filling for T equals 0, meaning no nearest neighbor, next nearest neighbor hopping. There is a only nearest neighbor hopping, sorry, if the T1 is different from 0. Mod Hubbard gap for all U greater than 0 is spin degenerate. However, for T different from 0, it's been metallic for all U greater than 0, spin split bands. Outer magnet that's metallic. So there must be something in between, like so metal insulator transition. This is what we would like to find. We don't find that, but the way we study this is to use effective quantum field theories that respect more or less the symmetries of the original models. And this is the idea is that if you are in the strongly correlated limit, for U much larger than the magnitude of the Hopper matrix elements, this maps at half-filling to Heisenberg antiferromagnet. And where these exchange couplings are given in terms of the Hopper in the U, this is well-known fact. And now, what is the quantum field theory? So the long wavelength limit for this theory is typically given for any Jij, you get something which looks like a free theory, but it's highly constrained. This is a free theory because it's only Gaussian, is the mu n square, is a nonlinear sigma model, but constrained. This what changes significantly the spectrum of this free system is that you have this hard constraint that the square of the direction of the magnetization is exactly equals to 1. So what is important for us in this talk? What are those ellipses here? Because this depends crucially on how these interactions are, right? It turns out that those ellipses in altermagnets are very interesting in the case, well, in many cases, but in the D-wave altermagnets. So if you look, that's the first term that I showed before. If you try to derive this from the Heisenberg model by path integral formalism or by any other method, so the first term for time this was shown was this paper by Helen Gomonai collaborators, where they took a classical Heisenberg model ruthenium oxide, ruthenium oxide or type of lattice, and they used the field equations for the classical limit U theta from a now Lifshitz equations, this term. So more recently, the paper that I'll give the reference not here later will derive this also from the Lib lattice. And the idea is, so this paper concerns classical solutions, right, for this nonlinear sigma model. And here our interest is basically what happens with respect to the usual quantum nonlinear sigma model if you quantize the systems. Quantize means here, I take this classical action here, which here is written, must emphasize an imaginary time. That's why I have an I here. And in the path integral formalism. So I make a sum of the histories. You compute the quantum fluctuations of this system. If the constraint here is implemented in terms of this delta function in functional space. Now, this is a quite difficult problem already in the absence of the altermagnetic term. So I will give you, I will show you only the spin wave theory here is some very simple renormalization group analysis for this part of the talk. In the next part, I will try to go to itinerant models because this is for a model for insulating altermagnets. So what I showed so far, the mean field theory was giving you only metallic states, right? Now, so what I'm doing here, I solving the constraint. So this is n has three components, right? I solving the constraint not using this, the n squared is equals to 1. So I solve this constraint by saying that one of the components is square root of 1 minus pi squared. The pi is a two-component field. So like that, pi x, pi y. And in order to facilitate analysis, if you are doing perturbation theory, I rescale pi by square root of g. Why am I doing that? So I'm doing that because I wanted to have one. This is the term was the standard spin wave theory for antiferromagnet. And this is the corrections that's a very complicated term, including the derivatives interactions. So this first line is just what is the standard quantum nonlinear sigma model that would follow for Haber model at half-filling, etc. But the altermagnet introduces a bunch of other terms, which is very complicated, but there is one crucial point here. Every G, except in this term here, every lambda multiplies a G. but not every G multiplies a lambda. So these terms are very higher order terms. Then it's very easy to guess what is a spin wave theory for altermagnets. You saw already this morning. The spin wave is very a bit found also. You just look in the Landau-Lifshitz equation, right? By linearizing the Landau-Lifshitz equations. So here in this language is very similar. Linearizing here means making this Gaussian. And how do I make this Gaussian? So I just imagine that G is small, but G times lambda is large. So I could just cross these terms because these terms are interaction, right? And the automagnetic term that survives here, which is Gaussian, but there's just two pi modes, is this. It's but there's three derivatives instead of two derivatives like the standard case. So this is your result. That's the Gaussian approximation. That's very simple to diagonalize. And this is exactly the limit when G, there is a limit, a kind of thermodynamic limit when this is exact, when G goes to zero, in lambda goes to infinity. You can see this because as I mentioned before, every lambda multiplies a G. This is a G squared times lambda. So this is very small. And G times lambda is kept fixed. Then you get that this is a limit, it's a theoretical limit, of course, where this becomes exact. So it's very easy to obtain the spectrum from the pole of the propagators of this, or just looking when this Lagrange vanishes. The difference from the usual antiferromagnet quantum original sigma model is that you have off-diagonal Green's functions also. So then, if you go to real time, you find the poles here, you obtain the spectrum that you saw. I don't know if you remember, but you saw already this morning, which has this D wave form. This is a spin wave spectrum of the D wave form, which is characteristic of D wave altermagnets. Now, in order to analyze the quantum critical point, so the first thing you can do is find the first corrections to this Gaussian theory. The first correction is more or less like we call in many-body theory, Hartree approximation. This means that I take this term here that I crossed here. First correction is to average of the square root of 1 minus G squared that I canceled in the beginning, right? So this term. So this involves the averaging of, you can expand this perturbative is 1 minus G. The average of pi squared is just have to integrate of the propagator. Right? If this gives you a first correction, you still have a D wave spectrum, but now this other parameter appears here, which shows that what happens at the quantum critical point. How is the quantum critical point defined? The quantum critical point is defined when this polarization, this magnetization here vanishes. And this happens when this average of pi squared is 2 over, this is determined by GC. So this, if you put this equal to 0, it's a trivial calculation to obtain the critical value. You see that the spectrum will just be the usual, at the critical point, only the usual antiferromagnetic spectrum, which has dynamic exponent equals to 1. So is this corroborated by renormalization group analysis? The answer is yes. So if you introduce a dimensionless coupling, G hat, in terms of some UV cutoff, which is proportional to inverse of the lattice spacing, and introduce a spatial momentum shell, you integrate over the frequencies or values of the frequency by momentum shell with some logarithmic length scale, you reduce the upper UV cutoff up to this infrared cutoff, which is lambda over L. Use the standard Wilson RG analysis. You obtain two equations. So lambda is the first I didn't mention before, but lambda is already dimensionless from the very beginning because n squared is equal to 1 is a dimensionless field. And by power counting, lambda has already 0 dimensions. And G has dimension 1 minus 1. There's two equations. We can see what happens. So this has a fixed point which is completely independent of lambda. Turns out that this fixed point corresponds exactly to the critical point I showed in the previous slide, except that here there is a factor of lambda for dimensional reasons. but it's the same critical point, right? The same fixed point. In this equation, if you linearize it, if you take this equation around this fixed point, you see that lambda decreases, it flows to zero. So this confirms that the quantum critical point, the universality in that case, at this order at least, is governed by the same fixed point as the standard quantum antiferromagnet derived from the Hubbard model of hard filling. So this is not the whole story. This is an initial analysis. There are indications that is much more complicated than that, but we still didn't finish this analysis because there are lots of subtleties related to what happens. For example, one of the subtleties that I can mention to you immediately is what happens in the boundary. For example, if you go to this by a trivial partial integration, right? Because you can look at this term, there's three derivatives, but there is something reminiscent from the Haldane topological term with the quantum nonlinear sigma model in 1 + 1 dimensions. And then you can imagine, okay, if imagine I have a boundary, you do simple partial integration. So I get in the boundary, if I have the boundary, I have exactly the Haldane term. Except that I don't have any reason to imagine a priori from knowing what's happening in the bulk that lambda should be quantized in the Haldane case. But it's possible that lambda flows to quantizer values. This is what we don't know. It could be that the boundary is just vanishing. So that is not clear. But if you forget that there is a bulk, lambda must be necessarily quantized. Because otherwise you have a complex, this is a topological term. You see? So this is an open question at the moment. We don't have the proof for that. Now, that said, so let's generalize a little bit more that idea. And now I will go back to this initial problem with the Lieb-Latze. He asked the following question. If I mix these ideas and the nonlinear sigma model with those pi modes and fermions, free fermions, you consider a Kondo interaction. Right? What happens? So if I go back to the Lieb-Latze, here is a different cartoon. These are like my blue sites, the A sites, which are non-magnetic. And these are where this black and white are the magnetic sites where I put spin up and spin down. Now, because of the hopping structure that we have hoppings, nearest neighbor hoppings for the non-magnetic atoms to the magnetic ones. And then next nearest neighbor hoppings from black to white. So this has a checkerboard structure. Clearly, you can replace this structure here by a checkerboard type of lattice that is frequently considered in the altermagnetic business. This is the free fermion theory, at the moment without any interactions. So let's analyze first this free fermion theory. So I will introduce some more indices here. The moment here you have the lattice sites and the spin degrees of freedom. So I will rewrite this a little bit because I have black and white sites. So that's I have to consider these two types of sites. I will add a new index here, grid index, which is black and white. You define this spin or CK, the momentum, black, white, and alpha, the spin. So the free theory becomes matrix theory, and you can solve it very easily. You get a theory that has, well, if you look at here, there are two things that happen. First, the Hamiltonian, the first quantizer Hamiltonian, this matrix that is here, is independent of alpha, independent of spin. Events are spin generated, C4 invariant, also due to the equivalence of black and white sites. Now, to lift this degeneracy, we'll add, this is also a model that was mentioned in the second talk. We'll add a Kondo interaction, which is similar to this Hubbard-Satonovich thing that we did in the beginning. So if you have a very large U, in principle, you can imagine that this Kondo term is realized here. Here there is not so that there is two Pauli matrices. There is this sigma spin Pauli matrix, and the others for the sublattices, right? Now, what is the mean field theory for this? I have to be quick here because how many minutes I have, Sasha? That's
2 minutes.
2 minutes. Okay, I have to be very quick now. So the mean field theory gives something. So if you do this mean field theory, you get direct like modes, but for spin up is for spin down. So here you can see one is spin up, which has the levels, these levels here, or energies for spin up. There are 4 nodes. For spin down, you have a pi over 2 rotator picture. So you see these red things are these Vegas peaks here. There's something in principle, this was known before. There are several papers that were considering this recently. Those momentum nodes. The question is what happens when you consider fluctuations are beyond mean field. This is the mean field for this quantum system, right? One important thing is that this mean field theory is not really a direct theory, traditional direct theory, Lorentz invariant, because there is a velocity and isotropy. There is a stronger isotropy than usually direct theory, the velocities are all the same. And here it is, they are not. There is a velocity and isotropy along the directions, comes from the lattice. Now, what happens beyond mean field? So beyond the field, I have to account for, I will consider 2 types of interactions. First, I go back to the nonlinear sigma model, which will control the fluctuations of the condor interaction. But here is again a pi modes, you expand this interaction, this S dot sigma, it up to pi square order. And I add a non-interaction because I want to consider also the interplay between spin charge fluctuations. And you will see why I'm doing this. So this is a Coulomb, long-range Coulomb interaction, but in 2 + 1 dimensions, this is not gradient of phi square. There's not the electric field. There is a magnitude of the gradient. This is also similar to graphene with Coulomb interactions. So you have to compute because of this anisotropy of the velocities. So the diagrams are very hard to compute. What I will show you. It's better to understand the basic idea because there are several functions of lambda. This lambda that I introduced here is not the same lambda as before, so I apologize for that. It's more or less the fine structure constant of the altermagnet is Z squared over V is related to Coulomb interaction. What you are looking here, want to see how these velocities that appear here will normalize. Why we're doing that? You want to see how the dynamic exponent is. Is this linear or not? Like in the standard direct theory, right? So even if you first, you will see that even if you start with the velocities isotropic, right? Well, they'll not be really all the time. If V1 equals V2, but it still will not be isotropic, okay? The V1 and V2 will, by fluctuations, be different anyway. The fluctuations bring this back to be different values. So, and then here I define 2 coupling constants. One is the Kondo coupling constant, and the other is this fine structure constant. I generalize NS is the number of Flavio-Flavos. He added the number of pi components. The physical case is NS equals 4, N equals 2. Now, let me tell you the results. So those functions, the details are in the paper. You see the QR code at the end. So if this I already said, that is V1s, even if I force in the beginning that V1 equals to V2, the fluctuations bring them back to be different. So in magnetic fluctuation Coulomb interaction, we have the competing effects here to determine the dynamic exponent. If I will determine the dynamic exponent, you look at the corrections for the diagram. So when you renormalize the velocities here with those complicated functions, where depending on the functions that appear here in this slide, and then I do a rescaling of the momentum variables and try to find what is the Z here. The Z is given by 1 plus maximum values of this gamma 1, gamma 2, which is now the question is when this is not universal. This is in general that depends on the quantum coupling. We don't know. Is not universal what this means. In the theory of quantum critical phenomena, universal means the integer numbers for the Z exponent, for the dynamic exponent. So in general, it's not an integer, but it's a natural question to ask what happens for this to become an integer. I have one more slide there, ready. What happens to this is an integer? So then I look at the value kappa G star square such that restores the value z equals 1. So then I find a series of graphics, I can plot a graph here for this constant and a function of lambda. These are all represent the critical couplings that makes z equal 1. But this requires some fine tuning. But in general, the z is non-universal. Before I end my talk, I will say, so there are open questions here. So there's what we don't know yet from this talk shows that there's a lot still open, many open questions. What's the precise nature of the quantum phase transition? There are several possible scenarios: altermagnet to antiferromagnetic insulator, altermagnetic metal to paramagnetic metal, which is another phase transition. The altermagnetic metal, altermagnet and or antiferromagnetic insulator. And this maybe symmetries, better, more in-depth study of the symmetries will rule out of some of those. There is one thing we did that I didn't have time to mention is the gap generation due to the Coulomb interaction. There is a metal insulator transition, because this was a question that I asked in the beginning. Is this always a metal or not? Well, it turns out we find, as in the appendix of this paper, we find that there is a gap generation, but unfortunately it's for large n, for a large number of pi mode components. Another open question whether there is possibility of the confinement criticality to spin liquid behavior that derived from altermagnets. This is something that Toshihiro Fakarasada is doing this. Then we'll leave there the conclusion. If you are interested in this paper, there is a QR code here. So thank you very much for your attention.
Since we have already a list of questions, maybe 1.5 questions. Do you have? Who wants to ask question?
Maybe just a simple question. You mentioned that actually gap generation is realized only at large number of flavors.
Yeah.
What is the reason for this? Because because usually at large number of flavors, actually we have strong screening.
Yes, yes.
And naively, I would expect that gap generation is suppressed.
Yeah, well, what we did is the following. There is this screening, but because of this is similar to, we did Schwinger dice equation. It is self-consistent Schwinger dice equation. As you see here from this slide, you have a Coulomb interaction in momentum space is 1 over magnitude of p. It's not 1 over p squared, because we're assuming like in graphene that's 1 over r for a still system. It is reduced. You don't have the same type of screening like you would have in 3+1. So that's a thing you know very well this, right? So that's like similar to QED3, for example. Yeah. That's how it is. But unfortunately, we didn't manage to do it for the low values of n. That was the thing. Yeah. But it's not excluded that it may happen.
Okay, then thanks. The speaker again.